Okay. What all topics did we talk about in the previous lecture? Can you remember? We talked about mean value theorem. We talked about continuous functions, differentiable functions, how to compute the first and second derivative of functions of multiple variables. We talked about mean value theorem. We talked about Taylor series. Okay, so one comment I did not make in the previous lecture, but I wanted to mention it today. So the spectral radius of a matrix A is continuous function of entries of matrix A. So spectral, remember the spectral radius rho of A is max over I, absolute value of lambda I. So this max over I, absolute value of lambda I, is actually a continuous function of the matrix. Okay, it's somewhat surprising result because remember these lambda i's are roots of a polynomial, right? So polynomial, so if you think about it, lambda I is root of determinant lambda I minus A. So I know that this determinant of lambda I minus A, that would be a continuous function of A. In fact, it would be a differentiable function of every element of A. But the cool thing is that the roots of that polynomial is also continuous in the entries of the matrix A. And then I'm not just taking the root, I'm looking at the absolute value and I'm taking the maximum of all those absolute values of roots. So it turns out that that is also a continuous function of the entries of matrix A. Okay, so kind of tying things together between what we studied in lecture 2 and what we studied in lecture 3. Okay, so that's just one comment I wanted to make, and then we'll start talking about convex function and convex set. Okay, that's the topic for today's discussion, after which we'll talk about local and global minimum of functions. Perfect. Any questions on this? Yes?
I think max is a non-linear operation.
It's a non-linear operation, but it's still a continuous operation.
Oh.
So if you have a vector x and you look at the function from x to max of x1, x2, xn. So x is a vector in Rn and I'm looking at this particular operation, it's actually a continuous operation. In fact, in one of the assignments later on, you will prove that if x was a positive vector, what that means is every entry is positive, then this is a convex operation. But we have not talked about convex function, which is what we are talking about today. But this is actually a convex function if x were a positive vector only. Okay? All right, so convex function and convex set. So let's start with convex set. How many of you have seen the definition of convex set before? Few people, okay. So what is a convex set? So let me draw two sets. One that looks like this, like an egg. The other set looks like, I don't know, a banana. So I have two things, egg and bananas. Which one of this is the convex set? Okay. So so let's think about it. So what convex set means is I pick 2 points within the set and I draw a line, straight line between them. So I pick an egg, I pick 2 points within the egg and I draw a straight line between those 2 points. The entire line segment actually lies within the set itself. Okay, now I look at a banana, I pick 2 points in banana and I draw a line, and it looks like the line segment is within the set. But then I pick 2 other points and I draw a line segment, and that line segment turns out to be outside of the set. That's not the case here. No matter which 2 points I pick and I draw a line between them, all these line segments are within the set, but that's not the case here. So this is a convex set, this is a non-convex set. Okay, let's think about a circle. A circle looks something like this. So remember that the interior of the circle is not part of the circle. Circle just means that the outer part of the sphere is in circle, and the interior is not part of the circle. You look at 2 points, join them, you see that the line segment is outside of the set, right? Because the interior is not included. In this case, the interior is actually part of the set. Okay, in this case, the interior is not part of the set, only the boundary is part of the set. So just because it looks like a convex set doesn't mean it is a convex set. You have to look at whether the interior is part of the set or not. Let's look at a 2-dimensional space, R2. I'm going to draw a line like this. So this is a line in a 2-dimensional set. I pick 2 points and I draw a line segment between these 2 points. That line segment actually lies on the line itself, so it's a convex set. Okay, so this is a convex set in R2. So these are the examples of convex set. It's extremely important concept from the point of view of optimization. A lot of optimization, interesting optimization problem is optimization over convex set. Okay, a lot of important optimization problems are optimization problems over non-convex sets. Okay, so to give you an example, suppose you go to American Airlines or Delta Airlines after you graduate from OSU, and you are required to optimize the scheduling of pilots and air hostesses and air stewards, okay, across the entire globe, right? That's a problem which is an integer optimization problem. It's a 0-1 problem. Either the pilot is there on a plane or not on a plane. Either the air hostess is there on the plane or not on a plane, right? And if an air hostess is on a plane, then he or she cannot be on other planes, right? So it's a 0-1 problem. And those 0-1 problems are non-convex optimization problems because your entries can be only 0 or 1. It cannot be anything in between. You cannot have half a pilot in airplane 1 and half a pilot at home. That doesn't make any sense. So a lot of important problems are non-convex problems. But the way to solve those non-convex problems would be to solve a problem over a convex set and then pray to the God that the solution would be in the feasible set. So things that we will talk about it in the future, but I just wanted to explain why this notion of convex set and non-convex sets are important from the point of view of optimization. We're using electricity, whether to turn on a generator or turn off a generator. So I know we don't think about electricity generation, but electricity generation is one of the important economic problems, especially of today. And whether you turn on a generator or turn off a generator is again a 0-1 problem. It's not a convex optimization problem. But once you have turned on the generator, whether it should generate at the minimum capacity or maximum capacity, that's a convex problem. Okay, because if the minimum is 100 megawatt and the maximum is 1000 megawatt, you can generate anything in between these two values. You pick 2 points in this set, you draw a line segment, it lies within the set. So it's a convex set. So typically in the case of a generator, the problem is you can have either 0 megawatt or you can have 100 megawatt. There's nothing in between. Okay, you can't have anything in between. But once you have it at 100 megawatt, you can go all the way to 1000 megawatt in somewhat of a linear fashion. Okay. By the way, there is a generator right next door. I don't know if you guys have seen it. It's right in front of RPAC. There is a big generator. It's at OSU campus, so I guess you have to go behind Baker and you will find that generator, that big building. You will see steam coming out of it in the winter. You see a lot of steam coming out of it. Anyone knows why that generator is at OSU campus? No? So it's because of reliability. So in case the transmission lines fail, that transmission lines that are coming to OSU, and that power generator will be turned on, and it will power all the critical components of OSU. So it'll power the hospitals, it'll power labs that are housing animals and bacteria and things like that. But it won't power our classrooms, okay? So it's not critical. Teaching is not critical, okay? There are more critical stuff going on at OSU than just teaching. So it'll power all the critical stuff. It cannot meet the entire demand of OSU campus. All right, so what's the mathematical definition of convex set? Okay, so we looked at the pictorial definition of convex set, but in this class we don't love pictures. We only love math. Okay, so I have a set X. It's a subset of Rn. I pick 2 points, x1 and x2 in this set X. I pick a value of alpha between 0 and 1. X is convex if for every x1, x2 in capital X, for every alpha between 0 and 1, alpha x1 plus 1 minus alpha x2 lies in the set capital X. So this is the line segment joining x1 and x2.
For all quantify is also a quantifier for alpha.
Yeah, there is a quantifier for alpha as well. For all x1, x2, for all alpha, this lies in the set capital X. Okay, any questions on this? That is all we need to know about convex sets. There's a very important theory of convex analysis that builds upon this definition, but we are not going to talk about that in this class. So this is all we need about convex sets. Typical examples are x equals to x such that ax equals to b, x equals to x such that ax is less than equal to b, x equals to x such that norm of x is less than equal to b. This could be any norm, so any LP norm. Remember we talked about LP norm in the beginning of this course on lecture 1. So any LP norm, pick any LP norm less than equal to b, that's a convex set. What else is a convex set? So x1, x2, xn convex, not xn, maybe like xk. Then intersection of xi, I equals 1 to k is also convex. So intersection of convex sets is convex, union is not. I can pick two spheres that are disjoint. I take the union, it's not a convex set. But if I take two spheres and I take the intersection, if it is non-empty, it's a convex set. Empty set is by definition convex because there are no points in the set. So it's convex by definition, but it's not an interesting convex set. Any other question? Yeah.
When you write AX less than or equal to B, are you just saying like each entry of the vector is less than B?
Yes, that's right. Okay, very good point. So when I say x is less than equal to y, what I mean is x1 is less than equal to y1, x2 is less than equal to y2, and xn is less than equal to yn. That's just the notation in optimization and linear algebra. So another set is a box set. So let me write it. X equals to x such that a is less than equal to x is less than equal to b. So this is actually a box. It looks something like this. So I'll give you the name. This is hyperplane. This is it's a convex region. I don't think it has a specific name. It's a sphere. This is known as a sphere. Let me write it. Hyperplane. This one doesn't have a name. This one has a name of sphere. This one has a name of box. So typically we will refer to something like I'm optimizing a function over a hyperplane, or optimizing a function over a box, or optimizing a function over a sphere. So that's how we use these terms. The only thing to remember is when we talk about sphere, typically in your mind, until this class, you would think of L2 norm, and so you will think of a sphere as a circle. But now with LP norm, sphere could look very different. So let me give you an example. So if it is R2 and L1 norm, then a sphere looks something like this. This is a sphere in L1 norm. This is a sphere in L infinity norm. So everything inside is included. Okay, so this is, both of these are sphere in different norms. Okay, any question so far? No? Okay, this kind of sphere is very important when we are solving problems of 0-1 type. So again, something we'll not talk about it here, but those of you who are graduate students in ISE, industrial engineering, you probably would be doing this L1 relaxation for the rest of your life. Okay. Awesome. No questions, then I'm going to erase all of it from the board. Perfect. Next in line is convex functions. So convex functions look something like this. This is my f of x. This is x on this side. So it looks something like this, or it looks something like this. Okay? And the idea in convex function is you pick any 2 points on the function, you draw a line segment, and the function is below that line segment. Okay? So I pick any 2 points, I draw a line segment between those 2 points, and this entire line segment has to be above the function, okay? So it cannot be below the function, no matter which 2 points I pick. It's above the function. So these are convex functions. Okay, so how do we write it mathematically? So I have a function f from Rn to R is convex if and only if for every x1, x2 in Rn, for every alpha in 0, 1, f of alpha x1 plus 1 minus alpha x2 is less than equal to there are multiple equivalent definitions of convex function. So let's write down what those definitions are. So this is definition number 1. Definition number 2 is epigraph of f, which is defined as xz such that f of x is less than equal to z is convex set. So this is basically, I draw a function okay, so this is my function f of x, and I'm looking at everything that's above the function f. Okay, everything all the way to infinity. So I'm looking at everything above the function all the way to infinity, and I want that particular set. That set is known as epigraph of f. And I want the epigraph of f to be a convex set. The third is f of x plus d is greater than equal to f of x plus gradient of fx transpose d. This should be true for all x and for all d in Rn. And the fourth definition is second derivative of f is positive definite for all x in Rn. So these are all equivalent definitions of convex functions. And depending on the context, we will use one of these definitions, various definitions. Yes.
Could you explain what epigraph is again?
So epigraph, so this is my function f of x, right? So I look at this space x cross R, okay? And I look at everything above the function going all the way to infinity. That's a set, that gives me a set, right? So that's a set of x comma z such that z is greater than equal to f of x. So this is my xz point. So this z point, this is my z. This z is above the function. This is my f of x, right? So z is greater than equal to f of x. So everything that goes all the way to infinity. that set needs to be a convex set. So everything above the function has to be a convex set. Typically these sets are unbounded sets, so it goes all the way to infinity. Any other question? This is the definition that we will not use, but I think it's important to understand the distinction between these definitions. So this is a set theoretic definition of a convex set, convex function, right? Because it transforms the convexity of a function into convexity of a set. Okay, so that's a epigraph. This one requires function to have real values. So in this case, you have you don't require a differentiable function in this case, right? So even if you have a real valued function like absolute value of x, this definition is satisfied. For third, you want the function to be at least differentiable once, because we are explicitly using the derivative of the function here. And for the fourth definition to hold, you want the function to be at least differentiable twice at all values of x in Rn. Okay. Now, of course, in this particular class, we are mainly concerned with functions that are infinitely differentiable. So these are these two definitions are the ones that we will use throughout the entire course. But these two definitions are very important if you were solving a problem that are somewhat abstract in nature, which some PhD students would do, but I'm assuming that undergraduates and master students will not really care about these two definitions, because we'll always be in this regime. Any question on this? All right. So with this, we are done with all the required preliminaries for understanding optimization. We've understood continuous functions, differentiable functions. Derivative of function is something that we'll use extensively throughout the course. So the first derivative and second derivative is something that you really have to get used to from now on. And we talked a little bit about convex set and convex functions, and those definitions are more than enough for us for the rest of the class. Oh, I think I should give you some examples of convex functions. X transpose Qx. Q is positive semi-definite or positive definite matrix. F of x equals to B transpose x. F of x equals to norm of x. Any P norm of x will do. Or maybe P norm raised to k. K is greater than equal to 1, and P is also greater than equal to 1. So P belongs to 1 infinity. These are all convex functions. Oh, the other thing is, if f1 to fn convex and alpha 1 to alpha n greater than equal to 0, then summation of alpha I fi is convex. These are all the definitions of convex function. If I'm not mistaken, max of fi's are also convex function. I'm trying to reconstruct the proof in my head. Yeah, I think this is true. So max over I of fi of x is convex. So various definitions of, various examples of convex function. Any questions so far?
For positive alpha terms.
Sorry?
Alpha 1, alpha, and they are all positive.
They're all positive. These are all non-negative numbers. Okay. Non-negative real numbers. Okay. Global and local minimum. So in this particular class, we'll talk about minimizing a function. Generally, optimization, some optimization books would be maximizing a function, some optimization books would be minimizing a function. So the convention in this class is we are minimizing a function. If you were solving a problem where you have to maximize a function, so I have to do max of f, then this is the same as I want to minimize negative f. Okay, so even if you are in a maximization sort of situation, you can just multiply the function by a negative sign and then you will be in minimization. So we'll just talk about minimization of function throughout the class. Okay, so x star is a global minimum of f, which is a function from Rn to R, then f of x star is less than equal to f of x for all x in Rn. So x star is a global minimum for a function if and only if f of x star is less than equal to f of x for all x in Rn. Let's look at an example. Exponential of x and x. It looks something like this. What is the global minimum of exponential of x? What is the point x star such that f of x star is always less than equal to f of x? Sorry?
Minus infinity.
Minus infinity. But remember, minus infinity is not part of Rn or R, right? So in this function, there is no minimum, no global minimum. So you could have functions that doesn't have global minimum. Okay? Another example would be log of x. I have x, I have log of x, which looks something like this. What is the global minimum of log of x? Well, you would be tempted to think that 0 would be the global minimum, right? Because that's where this function becomes minus infinity. But then this function doesn't take values in real line. Okay? So again, there is no global minimum of that particular function. So there are simple functions for which no minimum exists, no global minimum exists. But if a minimum exists, then this is how it is defined. So there is a global minimum if f of x star is less than equal to f of x for all x in Rn. We typically want this to have finite values and this to have finite values for all x in Rn.
Here, 0 is not in the
0 will not, yeah, because the function value is minus infinity. So it doesn't take values in R then in that case. Okay. Okay, so what's a nice picture of a function with a global minimum? let's look at x square. Nice looking function, looks something like this, and this is the global minimum. This is my x star. So I look at any value x. This is my x. This is my f of x. This is my f of x star. So f of x is greater than equal to f of x star. Okay. And this is true for all x in Rn. That's a global minimum. Let's look at another example. A function that looks something like this. So I have multiple points here. Let me call it x1, x2, x3, x4, x5, x6, x7. Yeah. So I've noted a few points that looks cool. Which one of them would qualify as a global minimum? x7, right? So the function value here, so this is my f of x7, and the entire function lies above f of x7. So x7 is a global minimum in this case. Awesome. So we all have understood what the notion of global minimum looks like. Let me write down about local minimum. So x star is a local minimum of f if and only if there exists an open set let me call it x Rn. X star lies in capital X such that f of x star is less than f of x for all x in capital X. Okay, so what are the local minimums here? Let's think about it. Which points seem to be satisfying that criteria of being a local minimum? So for every x, I need to find an open neighborhood around x1. So I found an open neighborhood around x1 in which the function values are greater than equal to the function values at x1. So I have x1 is a local minimum, x2 is a local minimum. I can find a neighborhood around which open neighborhood around x2. So the function is above f of x2 within that neighborhood. x3 is a local minimum. x4, is it a local minimum? No, because the function value is high. And if I look at a neighborhood around x4, the function value is below f of x4, so it's not a local minimum. x5 is a local minimum, x6 is a local minimum, x7 is a local minimum, and that's pretty much it. I have a bunch of local minima here. And by the way, these points would be considered local maximum, local maximum, local maximum, local maximum, right? Do we have a global maximum here in this function? Right? We don't have a global maximum because this function escapes to infinity on the other sides. So no global maximum, but there is a global minimum, there's a bunch of local minimum and a bunch of local maximum in this particular function. when people are training large language models or training machine learning models, all they are looking for is one of these local minimums, okay? Because the function landscape there is very, very complicated, and it has a lot of local minimum and a lot of local maximum. So what everyone is looking for is one of these x1 to x7 with, I mean, not looking at x4, so they are looking for x1, x2, x3, x5, x6, x7. Ideally, they want to be at x7, so they are putting in $500 billion to get to x7, but there's no guarantee that they'll reach x7, okay? So what that means is a lot of companies are putting a lot of money, billions of dollars, to get to one of these points. Oh, by the way, I went back and checked. So GPT-4 model had 1.7 trillion parameters. So not million, but not billion. It had 1.7 trillion parameters. So this N is 1.7 trillion. Okay. So I was wrong. It wasn't 700, 800 billion. It was 1.7 trillion. So anyways, big people do big things. We just talk about RN here. Okay. All right. Any questions so far? Okay. So the next question that we are interested in is knowing what a necessary condition for optimality is. And the necessary condition for optimality, some way you can, like one way you can think about it is if somebody comes and tells me that this is a minimum, it's a global minimum or a local minimum of a function, how do I check whether he or she is probably right? I just need to know a probable certificate that this particular person is right. It's not an absolute certificate. So absolute certificate would be sufficient condition. So we'll talk about sufficient conditions as well. But today we are talking about necessary conditions. So there is probability that what you are saying is right. Okay, so I have a function f of x star. This should be less than equal to f of x for all x in Rn. I want to come up with a certificate for x star, like what are the properties that x star must satisfy so that I'm kind of sort of assured, not with 100% guarantee, but I'm kind of sort of assured that this probably is a condition that is met by that x star. So we need to think about it. So let's do the following. I'm going to write x as x star plus alpha d. So I have f of x star plus alpha d is greater than equal to f of x star. Let me pick d to be in Rn and alpha to be greater than 0. So here is my x star, here is the direction d, and this point is x star plus alpha d. So I started with the hypothesis that f of x star is less than equal to f of x, which means x star is a global minimum. So this condition is obvious, it will be obviously satisfied. So I pick any direction d, I can go in any direction, And because x star is a global minimum, this equation will be satisfied. I am feeling a bit adventurous. So I am going to divide it by alpha. And remember, alpha is greater than 0, so this must be greater than or equal to 0. This holds true for all d in Rn and for all alpha greater than 0. These are all implications here. What should I do now? I'm feeling very adventurous now. So I'm going to take limit alpha go to 0. Okay, alpha is greater than 0, but I'll let alpha go to 0. So I'm going to take limit alpha goes to 0 f of x plus alpha d minus f of x star over alpha is greater than or equal to 0. Does it look familiar? What is this f of x star plus alpha d minus f of x star divided by alpha? This is actually gradient of fx star transpose d, which is greater than 0. How did I get this? Using Taylor series. Okay, remember we talked about Taylor series in the previous class. So by using Taylor series, I came to the conclusion that this particular statement holds for all d in Rn. For all d in Rn. Once I take the limit alpha goes to 0, then it becomes independent of alpha, right? So alpha gets eliminated and I'm just looking at something that's true for all d in Rn. And using Taylor series expansion and by taking appropriate limits, I have come to the conclusion that the derivative transpose d is greater than or equal to 0. So if it is true for all d in Rn, right? So minus d also lies in Rn. So if I pick a d and this is true, then I can pick a minus d also lies in Rn. So I have gradient of fx star transpose negative d is also greater than or equal to 0. Right? Because d is in Rn, so minus d is also in Rn, so this must hold true. So I have a vector transpose d which is non-negative and a vector transpose minus d is also non-negative. What does that mean? So it's a number, it's a scalar and the negative of the scalar. So both these scalars are greater than or equal to 0. That means the scalar must be equal to 0. So this implies that gradient of fx star transpose d equals to 0 for all d in Rn. Yeah. Okay, so I started with the condition that x star is optimal, x star is a global minimum, and I went through a series of assertions to prove that gradient of f at x star transpose d is equal to 0. And this is, by the way, this is true for all d in Rn. So in particular, it holds true for E1, E2, E3, E4 all the way up to En, because those are unit vectors in nth dimension and ith dimension, and that's also a vector in Rn. So what happens if I multiply the gradient of fx star transpose Ei? Del xi evaluated at x star equals to 0 for all I equals to 1 to n. Okay, in other words, gradient of fx star is equal to 0. So this is a necessary condition for optimality, that if x star is optimal, then the derivative of the function must be equal to 0 at that point. So I come to you, you give me a function, and I tell you x star, this is my x star. How would you know whether it is potentially optimal or not optimal? You will compute the first derivative of the function. If it is non-zero, you know that I'm lying, right? If it is 0, then I guess I'm right. But it's only a guess at this point of time. It's not certain that I'm right. So it's a good way to check whether someone is lying or not, but you can't be 100% sure whether the person is right. That's what necessary conditions typically do. Okay? Doesn't give you a certificate, foolproof certificate, but it does tell you whether a person is probably right or not probably right. So if x star is optimal, let me write it here. It's called first order necessary condition for optimality. First order necessary condition for optimality. X star global minimum if
I don't know how much you're technical class, but
x star is a global minimum implies gradient of fx star equals to 0, and the contrapositive statement if gradient of fx star is not equal to 0, then this means that x star not a global minimum. Okay, so the contrapositive statement, whatever is the conclusion here, you negate it, and whatever is the conclusion here, you negate it. Okay, and you get an implication. That's called a contrapositive statement. So the first order necessary conditions for optimality says that if x star is a global minimum, the derivative vanishes. Alternatively, if the derivative doesn't vanish, then x star is not a global minimum. Any questions so far? Okay. So when we are training large language models, or when we are training any kind of optimization, when we are using optimization solver, one of the things we look for to know whether we have reached close to the optimal or not is to look at the first derivative of the function. So we keep tracking the first derivative of the function, and as soon as the first derivative is close to 0, we say that looks like we are close to the optimal. We don't know yet whether we are at optimal solution or not, but at least we know that we are close to the optimal. So once we were doing a simulation, when we started the simulation, the gradient of fx naught, fx0 was 1 billion. We kept training it. We reached gradient of xk. It was around 1 million. 1 million is close to 0, than 1 billion. So we are close to the optimal. We are going in the right direction. Okay? So we are not going in the wrong direction. How do we know we are going in the wrong direction? I started with my gradient at 100, and at the next time step the gradient is 110. At the next time step the gradient is 120. We are going in the wrong direction. Something is wrong with our optimization solver. So we'll discuss all of these things in the next class. Thank you so much, and I'll see you guys on Monday, right? Yeah. See you on Monday.